So let's do the integral of the square root of e to the x plus 1. There's just one term in the entire integrand without any products or anything, so let's just substitute u equals e to the x plus 1 and see what happens. If we let u equal e to the x plus 1, then du equals e to the x dx. We would also like to find an expression for dx in terms of u. So if we divide e to the x on both sides, we end up with dx equals 1 over e to the x du. If we look at the relation u equals e to the x plus 1 and subtract 1 on both sides, we end up with e to the x equals u minus 1. So we now have an expression for e to the x entirely in terms of u. So this means instead of 1 over e to the x du, we can rewrite this as 1 over u minus 1 du, which means dx is equal to 1 over u minus 1 du. If we substitute this into the expression, this becomes the integral of the square root of u over u minus 1 du, since the square root of e to the x plus 1 becomes the square root of u, and the dx is replaced by 1 over u minus 1 du. Let's look at the integrand we have now in terms of u. There's a square root of u term in the numerator, and in the denominator, the u can be expressed as square root of u all squared. So let's just try substituting v equals the square root of u to deal with the square root of u term. If we do that, then dv is equal to 1 over 2 times the square root of u du. To get an expression for du entirely in terms of v, we should first multiply both sides of this relation by 2 square root of u to get du equals 2 square root of u dv. And since we let v equal the square root of u, 2 square root of u dv is just equal to 2v dv. So du is equal to 2v dv. We also need an expression for u minus 1 entirely in terms of v. Since we let v equal the square root of u, if we square both sides, we get v squared equals u. And if we subtract 1 on both sides, we get u minus 1 equals v squared minus 1. If we substitute all of this back into the integral of the square root of u over u minus 1 du becomes the integral of v over v squared minus 1 times 2v dv. Since square root of u becomes v, u minus 1 becomes v squared minus 1, and du is replaced by 2v dv. If we multiply the terms, this simplifies to the integral of 2v squared over v squared minus 1 dv, and if we take out the constant of 2 to the front of the integral, this is equal to 2 times the integral of v squared over v squared minus 1 dv. So let's look at what we have now. The integrand is a rational function with a quadratic denominator and a quadratic numerator, and we ideally want the degree of the numerator to be strictly less than that of the denominator. Since we have a quadratic denominator, we would like the numerator to be a linear term or a constant term, so the degree is strictly less than 2. We could use polynomial long division to split the rational function into a sum of a polynomial and a proper rational function, which is a rational function where the degree of the numerator is strictly less than that of the denominator. But I don't really want to do that, and instead I'd like to apply one of my favorite tricks. Why don't we just say that instead of v squared, we rewrite the numerator as v squared minus 1 plus 1, and this is still divided by v squared minus 1. This expression is equivalent because all I did was subtracted 1 then added 1 in the numerator. If we split this into a sum of fractions, we end up with v squared minus 1 over v squared minus 1 plus 1 over v squared minus 1 as the integrand. V squared minus 1 over v squared minus 1 just simplifies to 1, so this becomes 2 times the integral of 1 plus 1 over v squared minus 1 dv. The reason I subtracted 1, then added 1, is so I could have a v squared minus 1 term in the numerator, which would simplify nicely with the v squared minus 1 in the denominator. So now we have a sum of the constant polynomial 1 and the proper rational function 1 over v squared minus 1. Unfortunately, we still have to use partial fractions to deal with the quadratic in the denominator. We can factor the denominator and rewrite the rational function as 1 over v plus 1 times v minus 1. And now we just need to do the partial fractions to split the rational function into a sum of two smaller fractions. So here's how we do the partial fractions. We start with 1 over v plus 1 times v minus 1, and we set that to equal a over v plus 1 plus b over v minus 1, since the rational function we have is one with distinct linear factors in the denominator. If we multiply both sides of this equation by v plus 1 times v minus 1, we get the new equation a times v minus 1 plus b times v plus 1 is equal to 1. If we plug in v equals 1 into this equation, we get 2b equals 1, which implies b equals 1 half. If we plug in v equals negative 1, we get the equation negative 2a equals 1, which implies a equals negative 1 half. If we plug in these solved coefficients into the expression a over v plus 1 plus b over v minus 1, we end up with the expression negative 1 half over v plus 1 plus 1 half over v minus 1, and this is equal to negative 1 over 2 times parentheses v plus 1 plus 1 over 2 times parentheses v minus 1. So this means 1 over v plus 1 times v minus 1 is equal to negative 1 over 2 times parentheses v plus 1 plus 1 over 2 times parentheses v minus 1. Alright, so this means we can split the rational function and rewrite this as 2 times the integral of 1 minus 1 over 2 times parentheses v plus 1 plus 1 over 2 times parentheses v minus 1 dv. We have a sum of terms, which means we can integrate each term separately. If we do that, then we end up with 2 times parentheses v, which comes from the integral of 1 minus 1 half times ln of the absolute value of v plus 1, which is the integral of the second term, plus 1 half times ln of the absolute value of v minus 1, which is the integral of the third term. And after we close the parentheses, we have to add the constant of integration c. The entire expression in the parentheses is multiplied by a constant of 2 because there's a constant of 2 at the front of the integral. So if we expand this expression, this becomes 2v minus ln of the absolute value of v plus 1 plus ln of the absolute value of v minus 1 plus c. We originally substituted v equals the square root of u. So if we substitute the square root of u back in for the v, we end up with 2 square root of u minus ln of the absolute value of the square root of u plus 1 plus ln of the absolute value of the square root of u minus 1 plus c. We also substituted u equals e to the x plus 1. So if we substitute that back, we end up with 2 square root of e to the x plus 1 minus ln of the absolute value of the square root of e to the x plus 1 plus 1 plus ln of the absolute value of the square root of e to the x plus 1 minus 1 plus c. So as you can see, the final result is a pretty huge expression.